In the last two lectures, we have been discussing some of the properties of LTI systems, and in that context, we came across some of the properties of the convolution operation itself. And then we also looked at how to determine if a particular system has any of those properties or not by observing its impulse response, or in other words, we define what condition the impulse response must satisfy in order for the system to have those properties which we discussed, like the causality property or the invertibility property or the stability property, and so on and so forth. Okay, we discussed many properties up to the end of last lecture. Now, in today's lecture, we are going to talk about the response of an LTI system to a unit step input signal. So we call it as a unit step response. So far we have been focusing on the impulse response of the system. That is, what is the output of the system when the input is a unit impulse function. Now we will see what is the output of the system, that is for the LTI system, if the input is a unit step function. And by analyzing the output to the unit step, we will also establish a relationship between the unit step response and the unit impulse response that we have been discussing and are familiar with by now. Okay, so that will be the first part of today's lecture. And then we will move on to the next chapter, which deals with a very important topic of what is called as the Fourier series of periodic signals. So today I won't go into the specific implementation or the mathematical details of Fourier series itself, but I will lay down some fundamental concepts using very simple terms so that you can begin to understand what exactly are we trying to do when we are dealing with the Fourier series, and how this can be an important tool in the analysis of signals and systems. So that will be the latter part of today's lecture. So let us first talk about what is the unit step response of an LTI system. So we have depicted here an LTI system which has an impulse response given as h of n, and the input signal applied to it is a unit step signal. Okay, unit step signal is defined is having a value of 1 for n greater than or equal to 0. So n equal to 0, it has a value of 1. For n equal to 1, 2, 3, 4, and so on. And for negative values, it is 0. Okay, for n less than 0, u of n is equal to 0. So that's our unit step function, and if this is applied to the LTI system, the output that we get is called as the unit step response of the LTI system. So the output is basically the convolution of the input with the impulse response of the system. So now we can write that output as u of n convolved with the impulse response h of n, and that is the output of our system, which we generally represent as y of n. But since this is in response to a specific input signal, which is the unit step signal, we'll call it as s of n. Okay, so instead of y of n, that's our output, the general notation for output y of n, we call it as s of n now, because this is the output when the input x of n is u of n. Okay, so the input, which is x of n, is equal to u of n. So when the input is a unit step signal, the output y of n, we denote it as s of n. Okay, because it's a special input signal, we gave it a specific name. Just as we have the impulse response as h of n, the step response we denote it as s of n, which is the convolution between the unit step input and the impulse response of the system. Now we want to investigate this input-output relationship a bit deeper, and hence establish the relationship between the unit step response s of n and the unit impulse response h of n. So we call this s of n as the unit step response of the LTI system, which is the convolution of the unit step with the impulse response. And we can use the commutative property of convolution and write that as h of n convolved with u of n. So basically now we are treating this h of n as our input signal and this u of n as the impulse response. So s of n can be equivalently said as the output of the LTI system when the input is h of n and the impulse response is u of n. So in that sense, we can represent the system as the output of the system having this u of n as the impulse response and this h of n as its input signal. And if you recall, in the exercise that I gave towards the end of last lecture, which is example 212 from the textbook, if you read that, you will notice that a system whose impulse response is a unit step function, that is a system having u of n as its impulse response, is nothing but an accumulator or an adder, right? So the input-output relationship for the system whose impulse response is u of n is basically given as, so we can write the output s of n as a summation of the inputs. So in this case we are treating this h of n as our input signal. So the input-output relationship is going to be the output s of n equal to the summation of the input terms, which we call as h of k, for k equals minus infinity to infinity. And this fact will become clear to you when you read that example which I gave as an exercise at the end of previous lecture. So basically we arrive at this based on the fact that a system which has u of n as its impulse response is an accumulator or an adder, right? So that's basically the output is basically the summation of the input terms. So that is what we call as an accumulator. And a system which has this input-output relationship, the impulse response for that system is u of n. Okay, u of n is nothing but the unit step function. So basically what we see is that the output at any value of n is the sum of the inputs up to that value of n. So s of phi will be the sum of all the inputs up to h of 5, right? So s of n is basically for any value of n, so it will have the summation up to that value of n. Okay, so I need to make a correction here. Okay, this is up to n. This is an accumulator till the nth sample. So s of phi will be all the terms up to h of phi added together. S of 10 will be all the terms up to h of 10 added together. So that's what we call as an accumulator. And if you wanted to extract any particular value of h, for example h of 4, we just need to subtract the current sum with the previous sum, and we'll get the last value that was added to the sum. So for example, if we had s of 5, and from that if we subtracted s of 4, that should give us h of 5. So basically what we're saying is, suppose we had a sequence of numbers 1, 2, 1, 4, 3 and so on. Okay, if we add it up to this fifth number, so the sum is 3, 4, 8, 11, right? The total sum here is 11. Now, if we took this sum and subtracted it from the sum of the previous digits, that is excluding the last digit here, so that sum is equal to 4 plus 1 5 plus 3 8, right? So that is basically our S of n, and that is S of n minus 1. We have excluded the last term that we added, so the difference between these, we get it as S of n minus S of n minus 1, which is 11 minus 8 equals 3, which is the last term that we have added to this S of n. So we can recover h of n by subtracting S of n minus 1 from S of n, right? So that's the illustration to get this. So basically what we are seeing is that we can get back h of n. So h of n can be obtained as the difference of S of n and S of n minus 1. So that gives us some relationship between the impulse response h of n and the step response S of n. So if we know the step response S of n of an LTI system, we can find the impulse response h of n by doing this calculation, that is S of n minus S of n minus 1. That would give us our impulse response. And this follows very directly from the relationship between the unit step and the unit impulse functions itself. So if you recall, the relationship between the unit step and unit impulse function, which we did in lecture number 8, if you look at the video in lecture number 8, the relationship between unit step and unit impulse functions is, so the relationship between the unit step function and the unit impulse function is that the unit step function is a summation of shifted impulses, right? So when k equal to 0, you have delta of n. When k equal to 1, it is delta of n minus 1, that is delta shifted to the right by 1, and so on. So we have this relationship between the unit step function and the unit impulse function, and we did this in lecture number 8, if you recall from the video of lecture 8. Okay, and the step response and the impulse response have a similar relationship. So just as the unit step function is the summation of the unit impulse function, as a summation of shifted impulses, the step response S of n is a summation of the impulse responses h of k for up to that value of n. Okay, so that's basically the relationship which follows directly from the relationship between the unit step and the unit impulse function. So we see that the step response, or rather to be precise, the unit step response S of n is the summation of the unit impulse responses h of k for k equals minus infinity up to the sample number n for which we are finding the output S of n. Okay, so it's a direct consequence of the relationship between the unit step and unit impulse functions. Similarly, we can write the impulse function in terms of the step function as, again you can refer to this for in lecture number 8. So we can write the impulse function delta of n as the first difference of the step function, that is u of n minus u of n minus 1. So from that, the impulse response that we saw on the previous slide, the impulse response h of n is the first difference of the step responses S of n and S of n minus 1, right? So the impulse response h of n is the step response s of n minus the shifted version of s of n, which is s of n minus 1. We call this as the first difference of the step response. So the impulse response is the first difference of the unit step response. So the first thing we notice is that the unit step response is the running sum of the unit impulse response, which is what we have stated here. And the unit impulse response is the first difference of the unit step response. So we have stated this as well. Okay, so we have now established a relationship between the unit step response and the unit impulse response, and what we find is that we can find the impulse response h of n from the unit step response s of n. So if we know the step response, we can find what is the impulse response. And since the impulse response completely characterizes or describes the LTI system, therefore the unit step response also completely characterizes the LTI system, because from the unit step response we can compute the unit impulse response, and therefore using either of the two we can completely characterize the LTI system. Now we can extend these ideas to the continuous time as well. So far these relationships are applicable to the discrete time. What we have represented here are representing the discrete time systems, or the relations in the discrete time. We can extend these ideas to the continuous time case as well. So the difference is going to be instead of summation for the unit step response here, instead of summation of h of k, it is going to be integration of h of t to get s of t. So in the continuous time case, we'll have the step response as s of t. That will be equal to an integral of h of t from minus infinity to the time t at which we want to compute the unit step response. And from that we can find the unit impulse response as h of t to be given as s of t minus 1, which is the first difference of the unit step response. But rather than the first difference, the opposite of integration would be the process of differentiation, because we have here summation, so we use the first difference in the discrete time case. In the continuous time case, we are going to have the integral function here. So the integral, the opposite of the integral would be the derivative function. So we can find the impulse response as the derivative of the step response. So let's work that out. So for the continuous time case, okay, the relationship between the step response and the impulse response is the step response s of t is the integral of the impulse response, which we use the variable tau, d tau, for tau going from minus infinity up to the time t. Okay, so that's the relationship between the step response and the impulse response. So if the step response is the integral of the impulse response, it follows that the impulse response is going to be the derivative of the step response. So therefore the impulse response h of t would be the time derivative of the step response s of t, which we can simply write down as s dash of t. So now we have a relationship between the unit step response and the unit impulse response for the discrete time case as well as the continuous time case, where we see that the step response is an integral of the impulse response, and the impulse response is the derivative of the step response for the continuous case. And in the discrete case, the step response is a running sum of the impulse response, and the impulse response is the first difference of the unit step response. Okay, so that brings us to the conclusion of this particular chapter, and we have seen the different properties of LTI systems, how to characterize LTI systems. We have seen what is the impulse response, what is the step response now, and the relationship between the impulse and the step responses. And we've also seen how to find the output of a system given the impulse response of the system, both for the continuous case as well as for the discrete case. Okay, so that brings us to the end of this particular chapter. We will now be moving on to the next chapter, which deals with the frequency domain analysis of signals. And for a start, we will begin with the analysis, the frequency domain analysis of periodic signals. And for the periodic signals, the frequency domain representation is called as the Fourier series. And if the signal is non-periodic, we will call it as a Fourier transform. Again, we will go into the mathematical details of both in subsequent lectures, but the focus of today's lecture is going to be an introduction to what the Fourier series is actually trying to do. Without going too much into the mathematics behind it, we'll just try to understand what is the purpose of doing it and what information does the frequency domain analysis provides us, and what is the motivation behind it, and how it is an important tool that can be used for the analysis of signals as well as for systems. Okay, so we'll focus on an introduction to Fourier series in today's lecture. So let us first try to find out what exactly that we are trying to explore and what information does this topic of Fourier series gives us when we analyze a signal using the Fourier series. The first point that you need to remember is that when we go into the Fourier domain, okay, Fourier is the name of the mathematician who developed these techniques. When we go into the Fourier domain, the independent axis becomes frequency. So up to now, we have been talking about time as our independent variable. So that is in all our signals, the x-axis was the time variable. Now in the Fourier domain, the x-axis will be represented by frequency. So the analysis is going to be done in the frequency domain. So the first thing that we need to understand is that the analysis is in frequency domain. In other words, the independent variable that is on the x-axis is frequency. Okay, so basically by performing the Fourier series on a signal, or by computing the Fourier series of a time domain signal, we are basically converting the signal from the time domain to the frequency domain. So time domain to frequency domain transformation. Now, what information does this give us? When we convert a signal from the time domain to the frequency domain representation, what information does it give us? It gives us what are the frequency components that are present in the signal. So let's take a very simple example of a signal which we will call as x of t, and we will make the signal as the sum of say 2 or 3 different frequency components. So we now have this example signal which we call as x of t, and I'm taking the example of a continuous time signal x of t, and it is a sum of 3 different sinusoidal components having frequency 10 hertz, 15 hertz, and 20 hertz. So it's cosine 2 pi ft, cosine omega t, right? Omega is 2 pi f, so the frequency f here is 10. In this case here, for the second component, the frequency is 15, and for the third component, the frequency is 20. Now, if we had to plot the signal x of t, we may not be able to identify just by looking at it what are the different frequency components present in that signal. So we need to do the Fourier analysis to break the signal down into its constituent frequency components, and not just identify what frequencies are present, but we also need to identify what is the magnitude of each of those frequency components. For example, the 10 hertz frequency component has a magnitude of 1, the 15 hertz frequency component has a magnitude of 2, and the 20 hertz frequency component has a magnitude of 6. So we want to somehow figure out from the signal what frequencies are present in the signal. So if we are given a signal in the time domain, how do we find out what are the different frequencies, or what are the different frequency components that are present in the signal? To find that, we need to convert the signal from the time domain to the frequency domain by performing a transformation which is called as the Fourier transform or Fourier series. Now, the Fourier series specifically applies to periodic signals, and if the signal x of t is non-periodic, then the Fourier transform comes into the picture. So for a start, we will be restricting our analysis only to periodic signals, and therefore we'll be talking only about the Fourier series. And later on, we will move into the Fourier transform, where we start discussing about non-periodic signals as well. So for this particular case, cosine is a periodic signal, sine is also a periodic signal, and this cosine is also a periodic signal. So the sum of periodic signals is also another periodic signal. But by doing the time domain to frequency domain transformation, okay, how to do that, we'll talk about that again later. We can identify what are the frequencies present in that signal x of t and what is the magnitude of each of that frequency component. The other information that we also need to find out is whether that frequency component is having a cosine or a sine. Okay, a cosine corresponds to a zero phase shift cosine waveform, and a sine is nothing but a cosine waveform shifted by 90 degrees, right? So we also need to find the phase information, but let's keep the phase discussion to another time and focus only on the magnitude. So we are interested in finding out what are the different frequencies present in the signal x of t, and we want to plot that. Okay, so what we are going to do is we are going to make a graph which will depict the frequency components which are present in the signal and the magnitude of each of the frequency components. So when we plot this, we have our independent variable as the frequency. So what we have on the x-axis here is the frequency variable, and what we have on the y-axis is a function of frequency, and we are interested only in the magnitude. So we take only the magnitude component of that. So we call this as the magnitude response of the magnitude spectrum of the signal x of t. So x of t from the time domain is transformed to the frequency domain, so we get x of f, and the conventional notation is to write the frequency domain variable with a capital letter, and the independent variable of course is frequency denoted by f, and we are taking the magnitude of each of the frequency components. So if we look at this particular signal x of t, it has a frequency component of 10 hertz, 15 hertz, and 20 hertz. So there is no other frequency component present in this signal. So at 0 hertz there is nothing. So we have a component at, say, that's 10 hertz, we have a component at 15 hertz, and we have a component at 20 hertz. So the frequency here is in hertz, and we want to plot what is the frequency present in the signal and what is the magnitude of each of those frequency components. Now at 10 hertz, okay, at 10 hertz the magnitude is 1. So we will make an impulse here of height 1. So let me use black color for that. So at 10 hertz we have a magnitude of 1. At 15 hertz we have a magnitude of 2. So on the frequency axis at the point of 15 hertz, we are going to have an impulse of height 2, which is double the height 1. And at the frequency of 20 hertz, we have a magnitude of 6. So at 20 hertz, we are going to have the magnitude as 6. So that's much higher. Okay, so that is having a height of 1, that is having a height of 2, and that height, let's say that's 6. Okay, so this is basically the information that we are trying to extract by performing the Fourier analysis. We want to find out what are the different frequencies present in the signal x of t, and what is the magnitude of each of those frequency components, and plot them. And what we have plotted here is called as the magnitude spectrum. And since we have plotted this magnitude only on the positive frequency axis, it is called as a one-sided magnitude spectrum. As we will see later, we will end up actually having similar, just as we have at 10 hertz, there will be a component at minus 10 hertz, and a component at minus 15 hertz, and a component at minus 20 hertz. Again, we'll come to that later, but in a very broad sense, we are basically trying to find out what are the different frequencies present in the signal. So we see now that this signal is a summation of a 10 hertz component, a 15 hertz component, and a 20 hertz component. The 10 hertz component has an amplitude of 1, the 15 hertz component has an amplitude of 2, and the 20 hertz component has an amplitude of 6, or magnitude of 6. Okay, and by adding all these three frequency components, we get the signal x of t, and that is what we are trying to analyze and find out, and we call this as the one-sided magnitude spectrum of the signal x of t. The next thing that we notice here is that since we have constructed this x of t as a summation of sinusoidal signals, that is cosine and sine waveforms, and since the cosine and sine waveforms are periodic signals, the summation is also a periodic signal, that is x of t is periodic. And when x of t is a periodic signal, its spectrum x of f, that is its Fourier transform or Fourier series, is, if you notice here, this is discrete, right? Just as we had discrete signals, right, which are having impulses at integer values of the independent variable, right? So similarly, the Fourier series or the Fourier transform of a periodic signal is discrete in nature, and in being discrete, it is termed as the Fourier series. Okay, when it is not a periodic signal, when x of t is not a periodic signal, we will see that this spectrum is not periodic, but rather not discrete, but rather a continuous function of the frequency f. So now it is a discrete function of the frequency f. So that is a property that you will observe for periodic signals. When the signal is periodic in the time domain, it is going to be discrete in the frequency domain, and the transformation that we'll perform to go from the time domain to the frequency domain for a periodic signal is referred to as Fourier series. So that is what we have summarized here, that when the signal x of t, the time domain signal, is periodic, then the frequency domain representation is discrete, and the process of converting from the time domain to the frequency domain when x of t is periodic is called as the Fourier series transformation. Okay, so we perform Fourier series on the periodic signal x of t. We get its spectrum called x of f, which is called as the Fourier series of x of t, which is a periodic signal. Okay, so that gives us a rough overview of what exactly are we trying to find out when we are doing the frequency domain analysis, and when we are doing the Fourier analysis, that is, and what kind of information it is going to give us. So it's basically going to give us what is the frequency content present in the signal, and basically we want to find out the different frequency components that are present in the signal, and identify what is the magnitude of each of those frequency components as well. Or in other words, we want to break the signal down into its individual frequency components, so that when we add those frequency components in the right proportion, we get back our original signal. Okay, that's the whole idea behind it. And to illustrate this point further, I'm going to give you an example of a simple waveform, a periodic waveform that you are familiar with, which is a square waveform. And we will see that without proving it, I will show you that by adding a specific sinusoidal signals of specific frequencies, we can construct the square wave if we have sufficient number of those sinusoidal components. So let's see that illustration first to enforce this idea even strongly. So what we have here is a square wave, which is a periodic signal. Of course, it's periodic because it is repeating at regular intervals. So that's a square wave of some frequency, okay, and it's a periodic signal. And what we are basically saying is that we want to find out, okay, this is a square wave of some frequency, but this square wave is composed of many different sinusoidal signals of different frequency values. And when we add those different frequency sinusoidal components, we will get back this square wave. So just as we had this x of t here as a sum of sinusoidal components of certain frequencies, the square wave is now our x of t. So that's our x of t. Okay, and that is a sum of several different sinusoidal components, each having its own frequency. So that square wave is equal to a sinusoidal component of some frequency plus another sinusoidal component of another frequency plus another sinusoidal component of a different frequency plus, and it has many more terms. So if we keep adding all these frequency components, sinusoidal frequency components, it will give back our original square wave signal. So the periodic signal x of t is decomposed into its individual sinusoidal frequency components. So the first frequency component that we have here is a sine wave of frequency 1 hertz, right? So that's because it's completing one cycle in 1 second. The time axis here is 1 second, at 1 second here it has completed one cycle. So that's a 1 hertz signal. Similarly here, the time axis of 1 second is here, and in 1 second this waveform has completed 3 cycles. So that's a 3 hertz signal. And in this case, at 1 hertz it is completing 5 cycles, so it's a 5 hertz signal. So basically what we find is that a square wave signal is the sum of a 1 hertz component plus a 3 hertz component plus a 5 hertz component plus a 7 hertz plus 9 hertz and so on. And if we add many terms, in fact in this case we have to add infinite number of terms to get back this exact square wave shape. Okay, so basically the square wave signal is having a 1 hertz component, it is having a 3 hertz component, it is having a 5 hertz component, and further it will have a 7 hertz component, 9 hertz component, 11 and so on. And if you add all of these frequency components, each with its specific amplitude, then we will get back our original square wave, or the square wave can be broken down into its individual frequency components. So the process of converting this time domain signals representation into finding these frequency components is done by the mathematical process of Fourier series or Fourier transform, and because it's periodic, it is Fourier series. And basically, if you notice here, the 1 hertz component is having a specific amplitude which is 1 volt. The 3 hertz component is having an amplitude which is around say 0.35. The 5 hertz component is having an amplitude of 0.2. And likewise, if you see, each higher frequency component is going to have smaller and smaller amplitude. So we need to find out what is the amplitude or magnitude of each frequency component, and also find out what are all the different frequency components that are present in the signal. And the way to do that is to use what is called as the Fourier analysis. So by looking at only this signal, we wouldn't know that this signal has all these different frequency components. That is, it has a 1 hertz component and a 3 hertz and a 5 hertz and a 7 hertz and so on. So we are able to get that information only after converting this time domain signal into its frequency domain representation, and then we can figure out what are the different frequencies which are present in the signal. So to get information about the frequency content of the signal, we perform Fourier analysis. And for periodic signals, the process of Fourier analysis is called as the Fourier series. And again, what you notice is that because the signal is periodic, the frequency components that we have here are discrete. We have 1, we have 3, 5, 7. So between 1 and 3 there is nothing. Between 3 and 5 there is nothing. Okay, so it is having only discrete values of 1, 3, 5, 7, 9, 11 and so on. Okay, so when the time domain signal is periodic, the frequency domain representation will have frequency components which are discrete values. Okay, that's an important point that you need to bear in mind. Okay, still we are talking at a very high level overview of this concept without yet even diving into the mathematical background of this topic. Okay, so to illustrate this point further, I'm just going to represent the square wave which has been constructed by adding such sine waves. Okay, so I have shown here 3 components: 1 hertz, 3 hertz and 5 hertz component. If I add only these 3 components, what will the square wave look like? If I keep adding more and more and more terms like 7, 9, 11, 13, 15 and so on, in fact for this we need infinite terms. If we keep adding more and more terms, we will eventually get back our original x of t. Okay, and so to get it more accurate, we need to add more terms. If we add less number of terms, it will look somewhat like this, but not exactly like this. So let's see what happens with an illustration for that as well. So what I have shown here is the square wave reconstructed by adding these sinusoidal components. Okay, so if we add only the first 3 components, that is the 1 hertz and 3 hertz and 5 hertz component, we get this waveform. Okay, so it looks somewhat like a square wave, but it's not exactly square wave because you see these lines are not very vertical, and there are also these ripples where this should have been constant. Okay, so at the top here we have these ripples, and so this is basically the square wave which has been generated by adding only 3 components. So let me write this here. So 3 components. When we add more components, we get a much more better representation. So in the second wave on the top right here is the generated square wave when 5 sinusoidal components were added from the Fourier series. So that's with 5 components. Okay, with 5 components, we see that this this vertical line is much straighter than what we had here, and the ripples also become smaller. Okay, in the middle they become smaller, and that's compared to the previous one. And this waveform on the bottom left here is the square wave generated using 25 components. Again, we see now it is much more better represented, and the ripples have become much smaller. Although the frequency of the ripples is high, the ripples have become much smaller, and the vertical line is also much straighter in this case. And the last one here at the bottom right is a square wave synthesized using 250 components. That is 250 frequency components. Okay, so what we see is that as we add more and more terms to the series, we get a much better representation of our original signal. So to get exactly this waveform, we need to add infinite such components for this particular signal. Okay, for this particular signal, we need to have infinite terms. The reason for that is because we are trying to represent the sharp lines, sharp vertical lines using smooth curves. Okay, the sinusoidal components are smooth curves, but this vertical line here is a sharp straight line. We are trying to represent this sharp straight line using smooth curves. So we need to add infinite number of these waveforms to get this sharp line. Okay, again, that is something you will understand better once we go more in more details of this topic. But what I want you to understand very clearly is what exactly we are trying to do by performing the Fourier analysis or frequency domain analysis. We are trying to find out what are the different frequency components present in the signal. So that allows us to synthesize the signal. That means we can generate these signals by adding those sinusoidal frequency components. So by adding certain sinusoids, we are able to get back our original signal, and we can find out what are the different frequencies present in the signal as well. So that way we get information about the signal's frequency content, which is not possible to obtain by looking at it in the time domain. So we need to convert it to the frequency domain to get that information. Okay, so far we have just established what exactly we are trying to do in this particular topic of Fourier's analysis, and in Fourier series in particular, when we are dealing with periodic signals. Now the next thing that we need to focus on is what is called as the complex exponentials, because in the mathematical process behind this, we will be using the complex exponential signals, and we discussed about complex exponentials in our lecture number 3 video. So refer to the video of lecture number 3, and I'll just give you a quick recap of that here in the context of this particular topic. So as I said, the mathematical procedure for Fourier analysis is going to use the complex exponential signals, and recall from lecture number 3 that the complex exponential signal has the general form as x of t equals c e power a t, and for this to be a complex exponential, we have c and a as complex numbers. So where c is having a magnitude component, which we call as magnitude of c, and it has a phase component, which we give as e power j theta. So we are representing this complex number c in polar form as c e power j theta, and the complex number a in rectangular form as r plus j omega naught. Okay, we have done this process in lecture number 3, so you can review it very quickly in detail, but I'll just give an overview in the context of our topic of our discussion now. If we substitute these values into c and a, we get it as c e power j theta into e power r plus j omega naught t, right? So that's magnitude of c e power j theta into e power rt into e power j omega naught t, right? So that is something that we have seen in the past in lecture 3, and we did a specific case of this where we set r equal to 0. So that gives us a special complex exponential. So when r equal to 0, we get this as magnitude c. Let me write the full thing. When r equals 0, we get x of t as c e power j theta into e power j omega naught t, which we can write as the magnitude of c e power j omega naught t plus theta, right? So we have this representation, and for simplicity we can take this theta, okay, this theta term to be equal to 0, and we can make this magnitude c equal to 1. Okay, it need not be 0, theta need not be 0, and magnitude of c need not be 1, but just for simplicity we will take it as for simplicity we'll take magnitude of c equal to 1 and theta equal to 0, then our x of t becomes simply e power j omega naught t, which is cosine omega naught t plus j sine omega naught t. Now if we had c as some other number other than 1, that number would be multiplying these terms, and if we had theta to be not 0, then it will be cosine omega naught t plus theta plus j sine omega naught t plus theta, right? So just for simplicity, we have just to get rid of these terms, we have chosen the magnitude of c to be 1 and theta to be equal to 0. And an important property that we mentioned is that this e power j omega naught t is a periodic signal. Okay, so e power j omega naught t is periodic, and if it is periodic, then we can use the Fourier series to convert this to the frequency domain, to transform this to the frequency domain. So e power j omega naught t is periodic, and similarly the complex conjugate of that, which is e power minus j omega naught t, is also a periodic signal. Again, that is something that we mentioned when we were discussing this topic in lecture 3, and I mentioned at that point that this is an important property, and this complex exponential signal will be used in the analysis of subsequent chapters. Okay, so that is what we have arrived at this point of time. So e power j omega naught t, e power j omega naught t is a complex exponential, and e power j omega naught t is a periodic signal, and from this Euler's relationship, we see that the real part of e power j omega naught t is a cosine waveform, and the imaginary part is a sine waveform. Okay, so now we write that point as well. Real part of e power j omega naught t is a cosine waveform or cosine signal, and imaginary part of e power j omega naught t is a sine signal. And the next property that we talked about in this context is that e power minus j omega naught t is also periodic, with the same period as e power plus j omega naught t. Okay, so these are some of the concepts that we have studied earlier, which will be used in this chapter. So I'm giving a quick recap, and I recommend that you revise these concepts of complex exponential, and we will be using these signals in the mathematical process of Fourier series. Okay, and I'm going to stop here for today, and we will continue in the next lecture, where we will say why this e power j omega naught t, why these complex exponential signals are so important for LTI systems. And we will see that just as we had the unit impulse signal as an important signal in the time domain when we were dealing with LTI systems, the complex exponential is also an important signal because of specific properties that we will see in the context of LTI systems. So we will discuss all of that in the next lecture. So we'll stop here for today and continue in the next lecture.